I've mentioned it in some other contexts before. More or less, if you're conditioning on two things, conditioning A subject to B, if you get the same probability back, then B really didn't make a difference, right? Okay, so A doesn't depend on B, and mathematically, if we end up saying, they're products, okay, so if the products of their probabilities equals the probability of their intersect, then it's independent, okay, and that's a more textbook definition. We have not done an example yet, so let's do that, and hopefully you have a chance to look at this. Okay, so two standard dice are rolled. We have an event A, that the first die is a 6. B, the second die is an odd number, are A and B independent. Okay, and the way that all these problems operate is you just do the math. Okay, so you just verify that the probability of A intersect B equals the products of their individual probabilities. And we would suspect yes, right? Because the first die is rolled, and that's sort of what's going on with A, and the second die is for B. Okay, and those two dice are operating independently of each other. That's sort of how we feel. One does not influence the other. So we suspect yes, all right? Mathematically, we need to answer the question, is the probability of A intersect B equal to the probability of A times the probability of B? Okay, and it's just a matter of verifying that, even though intuitively it feels like yes, right? They should be independent. Okay, so the probability of A, first die is a 6. Well, that's a 1 in 6 chance, right? One good outcome for 6 total outcomes. Probability of B, odd number, there are 3 odd numbers out of 6, so that's 3/6 or 1/2. Okay, so we need to figure out what's in the intersection of these things. And we can just list out the outcomes, so let's do that. So this is, let's see, first die is a 6, so everything has got to have a 6 in front, and second die is an odd number, so 6/1, 6/3, and 6/5 should do it. Okay, so that's the probability of that set. And there are 3 good outcomes for 36 total outcomes, and that's a 12th, and it's looking good. Okay, so since the probability of A times the probability of B equals a 6th times a half equals a 12th, that equals the probability of A intersection B. We verified this, so they are independent. Okay, and this, again, just following our intuition, this seems right? Because the two dies are just different. They're different sets of outcomes that they're not tied to each other, right? Okay, so let's introduce a third event, C, that the sum of the dice is 11. Okay, are A and C independent? Okay, we suspect no, right? Because it seems like, well, this is referring to both of the dice, and A is just referring to the first die. And it feels like they're linked somehow. Okay, but again, we don't have to have any intuition. We can be dispassionate about this and just, find the probability of C, find the probability of A intersect C. Okay, so let's do that. Okay, so the probability of C, there are 2 outcomes. Okay, so there are 2 outcomes for 11. Okay, so they are 5/6 and 6/5. Right, so that's 2 out of 36 total, or 1/18. And, just multiplying, we could sort of skip ahead a little bit and just multiplying these 2 things in our head, like probability of A times the probability of C is 1/6 times 1/18. That's 1/108th. Dice probabilities or outcomes go in 36ths, so it's probably not going to work out. Okay, but let's just see what's in A intersect C anyway. Okay, so all the ones that, where the first die is 6 is this one here. So there's 1 outcome. Okay, so that's 6/5, which is 1 out of 36. And these 2 things are not equal, so the product of probability of A and probability of C is 1/108th, which is not equal to the probability of A intersect C. Okay, so not independent. Okay, questions about this? Yeah, not too hard, eh? Okay, so it should, this idea should follow your intuition, and I'll get to the notes on the next slide in a second. But I'm going to leave as an exercise, because there's another thing you can do, is determine if B and C are independent. Okay, so B is the second die is an odd number, and C is the sum of the dice is 11. Well, maybe we could just vote, maybe just to see, what you think these 2, if you think these things are independent or not. Do you want to do that, real quick? Okay, so do you think B and C are independent? Prepare to vote. Okay, you ready? Okay, who thinks they're independent? Who thinks they're not? Okay, most of you think they're not. A handful of you thought that they were, and you should try it. Okay, you should try the math. Let's just see if we can do the math real quick. Probability of B is a half. probability of C is an 18th. So multiplying those things together gets us 1/36th. And B intersects C. Let's see, B is the event is an odd number. So that's the only outcome here. Okay, it's 6, 5. Okay, that's the only outcome. So that's 1/36. They actually are independent. Okay, which seems a little tricky, right? It seems a little tricky. So let's see if we can codify this just a little bit, because my notion of independence is sort of like, these two things are operating much like the rule of product did. Okay, or much like when we were writing computer code and we call, Randon and Bernoulli, they don't depend on each other. Independent. They're independent trials. Okay, so that is the assumption that we're using there, and that is what independence feels like to me. That there are like independent blocks of code that are running. Okay, why do I say it's similar to the rule of product? Well, the rule of product has that feel as well, where you're trying to scale up outcomes, right? Remember the rule of product, you say, event 1 has M outcomes, and event 2 has N outcomes, and they always have N. They don't have to be the same N, but you always have N outcomes no matter what. What happens in event 1? Okay, so you get to multiply M times N. Okay, that's the total number. So, in terms of the dice roll-y thing, A has a 6. It's, but the probability is 1 out of 6, right? So you're sort of scaling up the numerator and the denominator. Okay, so the probability scales up, and you multiply by, B is, second die has an odd number, right? There are 3 possibilities out of 6, so you multiply, it's sort of multiplying the numerator and denominator simultaneously. Okay, so it sort of has that same feel, but the textbooks and, my definition up here also says that they're independent in this coincidental way, just like we sort of see with events B and C, and we'll see other examples as we go on with this, that, doesn't really feel like independence. Anyway, it is independence, but it's a little counterintuitive, and I don't have a good remedy for that. Okay, so just be on guard for that. One thing I just want to mention as a star, lots of people, your predecessors, okay, so past students, find independence and mutual exclusion to be confusing. They seem to interchange one for the other, all right? So just be careful. Independence is not the same thing as mutual exclusion. Okay, mutual exclusion means that A and B are disjoint, they don't overlap. That means something very dependent, actually, okay? So if A happens, then B is known not to happen. Okay, so that's a very dependent relationship. If you know that A happens, you know that it's B is never going to happen, and vice versa. Okay, the only way that you can have both of these things at the same time is if you have a null event, which is not usually very exciting to examine. So if it has a probability of 0, the way the math works out, it will be both of these things, but that that doesn't happen very much. Okay, so just make sure that you don't confuse these two things. And as much as I warn you, some of you are going to confuse them, but this is a particular pain point that I need to warn you about. Okay, I'm going to skip a couple slides. We don't need to do them today, and I want to talk to you about randomized algorithms. And the reason I'm doing this is because I want to get through the primality testing, and if I do those 2 slides, we're not going to have enough time. Okay, so we're going to go to slide 8 and talk about using randomization as a tool. Okay, and first I'm going to talk about sampling. All right, you can use sampling to make your algorithms easier. Okay, so here's one thing. Okay, so say you're asked to measure the area of an island out in the sea somewhere. Okay, so you can do this in an analytical way. Okay, so you can write an algorithm or that does the calculus, or you could do the calculus yourself. Okay, so you could carefully, use cartographic techniques. Oh boy, I'm using big words. Okay, and you can calculate the area using calculus. You can sweep your bar across, okay, and add up all the little bits and pieces. You can be very, very precise. Or you could use sampling, okay, and the short way is you pick a bunch of random points in this map. Okay, so that's good enough. And you count the number of times you hit the island. Okay, and you take it as a fraction of the total rectangle. Okay, as an estimate. Now it's not going to be exact, but it's going to be fairly close. The more sampling you take, the better the estimate's going to be. Okay, so select n points from the rectangle, and k of them fall within the island. Okay, so you estimate the area of the island as the fraction of points that land in the island multiplied by the area of the rectangle. won't give you an exact answer, but it will converge on the exact answer. Okay, okay, what about A/B preferencing? So this is very topical around election time when people are, they're polled, right? What do the poll numbers say, right? So you take a sample of these people, right? There's 50 people there. Some of them are, they're going to vote red. Some of them are going to vote blue. The long way of figuring out this is to ask everybody. And you get an exact count. And the short way is to ask a small sample or a smaller sample. And those people will give you an estimate of the probability that the population will say or prefers A. Okay, so estimate the probability of A is the number of people who say A divided by N. Okay, and this doesn't have to be about politics. It could be about you can do A/B testing on website designs and other automated things. Okay, that Facebook wants to make something a little bit better in their design. They give you one version. They give other people a different version. Okay, and see how you react. Okay, so lots of applications for this. Okay, but anyway, that's the short way. Okay, using sampling. There's another one for math. Here's this math problem. It doesn't seem like it's too hard, like you could have done this in high school. It's just that it takes you a long time to verify this. Okay, if you want to verify that this expansion is actually correct, the long way is to do the expansion yourself. Foil it. I hate foil. I hate that thing. But first, outside, inside, last, right? 2 brackets generates 4 terms, right? 3 brackets generates 8 terms. Okay, 4 brackets would generate 16 terms, and the more brackets you have, the more terms you get, and it grows exponentially. So an exact answer is possible, but it might take you a while. Okay, exponential time in general. The short way is to use sampling, and what you can do for sampling is sub in some numbers. Okay, so and verify, because to do the calculation is cheaper than to do the expansion, right? Especially if you sub in 0. Like, let's just check to see if 0 works. So it's 7 times 1 times 5 times 3. So that's 20, 30 counts. 105, and here's the 105 over here. Okay, well, minus 105 because there's a minus sign there. Okay, so it seems to work at x equals 0. And maybe x equals 1 is also easy to verify. Anyway, you try a whole bunch of different x's until you get bored that, it agrees. If it ever disagrees, that is conclusive proof that it's not right, right? Right. Okay, so sub in some random values of x and check equality. And if any one of them fails, that's conclusive proof that it doesn't work. And so you have a bunch, if it works, it might agree. You just happen to agree at that spot. So you might believe that it works, but maybe you should do more data, get more data. This technique of keeping on trying things until you're bored is called a Monte Carlo algorithm. And I'll talk a bit about this on the next slide. Most of the algorithms that you have written in your life have been deterministic in that there are no branches in the sequence that don't depend on the input. Okay, you can change based on the input, but once your input has been given to you, you're sort of locked in, right? Okay, there are no choices. Okay, but a randomized algorithm, you're allowed to toss a coin at various steps and then react based on what the coin told you. And weirdly, there are algorithms that the only known or best solutions use coin tossing, strangely enough. Okay, so one of them that you might have coded in one of your coding courses is quicksort. Okay, and so if you've coded quicksort before, the strategy is to pick a random pivot. Okay, so you pick a random pivot, or you can just randomize the array before calling quicksort, which I know seems a little strange to create more work for yourself, but it's the randomization that keeps the running times on average pretty good, right? It keeps it to n log n. Sometimes pathological things occur, right? And you end up picking the wrong pivot consistently throughout the running of your algorithm, and ends up getting an expensive running time, like an n-squared running time. Okay, anyway, this, I'm getting a little bit ahead of myself. This sort of algorithm is known as a Las Vegas algorithm. Okay, something that's efficient on average, but can be inefficient in a particular case. It might actually run forever in the general sort of Las Vegas algorithm. Okay, so it could have an expensive running time, but on average, it's an efficient running time. Okay, and there's another type of algorithm I just mentioned, Monte Carlo algorithms, that are allowed to be wrong. Okay, so in terms of algorithm science, computer science of what can be done. People talk about P and NP. This famous problem: does P equal NP? Famous open computer science problem since the 1970s. Anyway, there are other complexity classes that describe. P means all the algorithms that can be solved in polynomial time. Anyway, there's one called ZPP. Okay, so these are all the algorithms that admit an efficient solution using coin tossing. Okay, so there's this conjecture that if you can solve it using coin tossing efficiently, you should be able to find a deterministic algorithm that works. And we're going to talk about primality testing today in great detail. This is probably the very first and famous randomized algorithm that was found to be efficient, and they did not find a deterministic version until about 20 years ago. And it's not that efficient, actually. They don't use it. I think it's like n to the 6th or something like that. It's not a very efficient algorithm. Anyway, but it's polynomial time, so they say it's efficient, but it's really not. Anyway, this Monte Carlo algorithm is allowed to be wrong with some small probability, and you're allowed to tune it to whatever your tolerance level of wrongness is. But whenever we want some small number, we usually use epsilon. Okay, so epsilon is a small but non-zero number. Okay, and I'm going to show you how to get epsilon down to as small as you like using a technique called probability amplification, and it uses independence as a driver. All right. So without any further ado, let's do an example of this. Okay, by talking about a circuit, okay, or a machine. Okay, so suppose a machine has two independent components, and I've drawn it up here as sort of a circuit where you find a path from A to B, you're good. Okay, and the machine is okay as long as there is one path. So each component breaks with probability P, so in this case it's only going to break if both of the pieces, both of its components break. Okay, so what's the probability the machine breaks? Well, they're independent. Okay, so these things scale multiplicatively. Okay, so if E1 is the event that component 1 breaks, and E2 is the event component 2 breaks, then we're just going to multiply P and P together. Okay, so the probability that E1 and E2 occurs, okay, so both of these things break, equals the probability of E1 times the probability of E2, and this is by independence, and each of these has a probability of P, so we get P squared. So this is a machine that has some redundancy. It has two different paths. Okay? So what if we had k different paths? So what if I drew a whole bunch of these things in through here, and there were k parallel components? What would be the probability then? P to the k, right? P to the k. Because all of them would have to break simultaneously, right? And they're all independent of each other, so they all scale up multiplicatively. Yeah? Okay, and mathematically, we would write that it's E1 and E2 and EK. Maybe it's better that I do it this way, like you have this thing. Okay, and start using our notation a little bit here. Okay, but it's a whole bunch of intersects, and they're all independent. They're all mutually independent of each other. Okay, so they all multiply. So this becomes the product of the individual probabilities. And that's P multiplied by itself, K times over, and that's P to the K. Okay, so far so good? Now, some of you might be wondering, like, how do we get the smallest arbitrary epsilon that we would ever want for an algorithm by using coin tossing? Okay, I mean, it seems like having a wrong answer would be catastrophic, and you might be right, but the solution is to use this. Okay, so we're going to have k independent components, and only if all k of them break simultaneously will our answer be wrong. Okay, let's get to it. Prime numbers are really important for our crypto systems. RSA cryptography is what most of SSH and most of our encryption uses. Maybe some people don't like it that much, but it's everywhere, and it's pretty good. And it uses large primes, okay, the product of two very large primes to make sure everything is secure. Right? The problem is, how do you find large primes? And as the numbers get large, naive algorithms don't work. Okay, so here's a naive algorithm that you probably saw in NACA 101, and it is the following. So suppose you just pick a random bit string, say that's 1,000 bits long. Okay, so big number, and you want to determine, is it prime? Okay, so what you can do is you can sort of divide and test, and test a whole bunch of numbers all the way up to root n. Root n, and not n minus 1. This is a slight optimization, because if n is composite, you're going to trip over a factor by the time you get to root n. And that's because there's a conjugate larger factor. Okay, so you can stop searching after root n, which is a nice optimization. Okay, so if n is composite, there is a non-trivial factor that's less than or equal to root n. And, if you're just doing divide and test on your calculator, this can save you some time, some sweat, right? So, if you want to test, is 1,023 prime or not, okay, you only have to go up to 31. Okay, and then you can, or up to 32, I guess, and then you can quit. Okay, so there's a lot to be said. There's a lot of fewer iterations to go through for that. Okay, but still, the running time is big. And when you talk about calculating running time, it's always a function of input size. Input size is not what you think it is. Okay, it's not n. All right, n, the input size is actually like you don't need a lot of room to express n. Right. So how many bits does it take to express n? That is the input size. Okay, and the number of bits to express n is the log. Let's say it's pretty close to log base 2 of n. Okay, so and if you invert this, this means that n is around 2 to the beta. Okay, so even with this nice optimization, the number of iterations to prove that n is prime, we have to check big O of root n of these things, and the input size is actually beta. So this is square root of 2 to the beta, and doing some power rearranging here, this is actually root 2 to the beta. And root 2 is 1.4 something, but that's exponential. Okay, so it's something to the beta. That's exponential running time. Okay, so this is not an efficient way of going here. And in fact, by being clever, you can actually figure out if the number is prime by, well, you'll see in a moment. Okay, you can determine is the number prime without actually finding the number's prime factorization. Okay, so it is largely believed in the community, and this is a good thing for RSA because your key, your private key that you hold dear, you need the product of two very large primes. If someone can factor those very large things, then you're in trouble. Okay, so if factorization turned out to be easy, then all of your email will be readable, which is probably embarrassing. No, it would be for me anyway. Okay, so factoring is a much harder problem probably than primality testing, okay, which it turns out is tractable. Okay, primality testing is in P. Okay, so polynomial time. Okay, so what do we do? Well, somebody referenced some work of Fermat. All right, so Fermat's got his name on a bunch of things. And one of the most famous things is Fermat's little theorem. Okay, so his little theorem comes into play, and it says that if p is prime, then every integer between 1 and p, but not p, okay, if you raise it to the exponent p minus 1, and then run mod p on it, you'll get 1. Okay, and this works for every number between 1 and p minus 1. Okay, so if p is prime, then this will work out for every single number. Cool. It turns out that doing mod is pretty cheap. Doing exponentiation is pretty cheap if you have the right algorithm. You can do fast exponentiation by taking successive squares, okay, and just square, 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 and mod along the way so the number doesn't get too big, because multiplication and addition are closed under mod. Okay, so you can do this really quickly. Okay, so this suggests a factorless test, and what you do is you create a box, okay, some function, and you pick some a, maybe at random, say, and then you ask the question, is a to the n minus 1 equal to 1 mod n? And if the answer is yes, then n is prime. And if the answer is no, then n is composite. Okay, this seems like it has a lot of potential, right? There's only one problem with this. This is an if-then, and it's not an if and only if. So in other words, if you find that this is not true, okay, so if a to the n minus 1 is not equal to 1 mod n, then you know it's not prime, for sure, because it's got to work for every a, but it didn't work. Okay, so you know that that's like a counterexample, right? So you find the counterexample. It's actually, it's called a witness, Okay, so it's actually there to say, okay, it's, no, this is proof that it's not prime. But if it happens that it works out to be 1, it might be prime and it might still be composite. Okay, because not every number will generate will be a witness. Not every one will be a witness. Okay, so we might not know. Now, without getting into the gory details of number theory, there is a pretty quick proof, all right, that I'm not going to show you because that's, again, we need number theory, and it's not a course in number theory. But the chances of picking a witness is at least half. Okay, so it's actually way better than a half. It's probably like 75%, okay, or maybe 90%, something like that. There are a lot of witnesses for most numbers. Okay, but anyway, a half is a good number for us. Okay, because it allows us to sort of process this as another type of problem. Okay, so what do I mean? Okay, so for most composite, at least half the possible A's are witnesses. Okay, it's usually a lot more than half. Okay, but half is good enough. Okay, so the probability that the Fermat test returns a yes if n is prime is 100%. Okay, so it works for every single thing if it's a prime. And the chance that it returns a yes if n is not prime is less than or equal to a half. Okay, it's probably a smaller number than that, but a half is good. And the reason I want to deal with a half is because coins work in halves, right? So imagine you toss a coin and it comes up heads. Okay, well, heads is inconclusive. Okay, but all right, we toss it again, it comes up heads. Okay, it comes up heads, comes up heads. Okay, so after how many times does it come up heads do you start believing it's a two-headed coin? Right? Okay, so how many times do you flip the coin? Well, you flip it k times. Okay, so what if you tossed a coin k times in a row and got heads k times in a row? Okay, well, that's exactly what this routine does. Okay, so you randomly pick some integers less than n. You do a Fermat test. If it fails, then you know that it's a composite and you quit. You return false. But if it passes all k tests, then you say, this is prime. Now, you might be wrong, but the probability that you're wrong, you can tune it to make it as small as you would like. Why? They're all independent trials. Okay, so the probability that is prime returns yes equals the probability that all k return yes on AI. Okay, and n is not prime. Because they're independent, this is equal to, this is the product of all the probabilities of yes on AI. And this is a half times a half times a half times a half. Okay. K of them there. Okay, 1 over 2 to the k. Okay, so you can just pick your number of trials as high as you would like. And you can just say, okay, well, I'll pick it so that it's more likely that the Earth is about to explode by a cosmic ray or something like this. It's like 10 to the 68. You can tune k however you would like. Okay, but in practice, you're going to trip over a witness pretty quickly. Like usually 2 and 3 are sufficient as tests. There are a couple of gotchas here. One is there are some pathologically bad numbers out there that will not yield a witness that is co-prime to n. Okay, so will return 1 for the whole thing. These are known as Carmichael numbers, and there's an extra special piece of code in the algorithm that's set aside for that. So there's a little bit more to this algorithm than this, but this will be correct for everything except for those Carmichael numbers, which is really cool. Okay, so this is the technique of probability amplification, and this is what I mean by, you can be wrong, but you'll be wrong with vanishingly small probability. You can make this as small as you would like. Okay, so this is our epsilon. Okay, so a Monte Carlo algorithm similar to the k-parallel components. Cool. Yeah? Okay, questions about this? Sorry? No, epsilon is 1 over 2 to the k. Yeah, it's not just 1 over 2. I don't think we would be happy with just a half, right? But 1 over 2 to the 100, maybe we'll be happy there, or 2 to the 200. Yeah. Isn't this cool? Like, this is one of the. I love this sort of thing. You're rolling dice you're flipping coins to try and find prime numbers, and prime numbers seem like, I don't know. There's an infinite number of them. They seem like they're maybe hard to find, but this is yeah. type of algorithm in practice ever fail? No. So when you make your SSH keys for whatever system you're using, it uses this algorithm to find prime numbers for you. Yeah. So this is the industrial algorithm that's used. This last one here, this is our epsilon. Okay, this is our. Oh, why does it have to be prime numbers for your SSH? Okay, so this requires a lot of number theory math. So, yeah, look up. Let's see. So look up RSA. Okay, so RSA. What's that? Well, I mean, it is and it isn't. So I don't cover it in my Macam 101, for example. So yeah, so maybe you've seen RSA in Macam 101, and if you haven't, you can look it up. It requires the product of two primes, P and Q, two very large, roughly equally sized primes, and if you can factorize P and Q, then yeah, you can break the system. Okay, so but it requires two primes. Sorry. Okay, I'll let you look it up because there's like probably a lecture and a half worth of math that is required for this. Okay, so but you can look it up. It's in your Mac. I think it is in your Macam textbook if it's Grimaldi. I think they talk about it there. So. Okay, that's all I brought. The rest of this week we're going to finish this unit. There's another randomized algorithm that uses probability amplification. We'll see that probably on Friday. Okay. Anyway, we'll see Wednesday first. I can give you a mathematical definition. So the complexity one, we consider the polynomial time algorithms to be practical. Anything that's not polynomial time, exponential or higher, is infinite. So it may or may not be the case because into the sixth algorithm is not necessarily the best use of time as a scale, but it's scaled way better than exponential. So that's sort of the dividing line in computer science complexity.